immortalize the animalness on YouTube. Okay. Now, what I covered on Monday is pretty tough stuff to absorb, and I point that out because what I'm going to cover today is even tougher. Fortunately, whatever homework problems come from this part of Chapter 5 would not really require knowing like all of the details of these methods. So I think those problems are mainly about coding the algorithms that are already there. But still, there are a lot of key ideas in terms of how algorithms in numerical linear algebra can be made more efficient or be improved in some other way. And so some of these ideas can be applied to other problems too. But and that's what I'm going to emphasize here. So I may not have time to get through every little detail, and actually probably none of us want that to happen anyway because it gets pretty ugly. It does get pretty ugly, but we'll just we'll see how this goes. All right. But this is we're going to see today one of the most important methods in numerical linear algebra. Okay, so I temporarily forget how to share screen. Okay, the conjugate gradient method, a method so popular they threw a party for its 50th birthday. Now, when it comes to academics, party means conference, but there is still alcohol involved. And this method was developed in 1952. So in 2002, they held a conference in honor of the method's 50th birthday and also my advisor Gene Golub's 70th birthday. So, and actually, I'm not aware of other methods that have been celebrated in that manner, but I'm sure it's happened. Okay. But what we're going to see is an attempt to improve on the method from last time, Lanczos iteration. Okay. Not sure we'll have a LaTeX error already, but okay. All right. So we're still in a situation of solving AX equals B, asymmetric positive definite. And for that purpose, we saw steepest descent. That didn't work so well. Now we have Lanczos iteration, which is an improvement. And just to recap, every single iterate that Lanczos produces, xk, has this form as the initial guess, plus a linear combination of some orthonormal vectors that actually are parallel to the residuals. And how do you get the linear combination? How do you get this yk? Well, you're solving this system of equations, where tk is a k by k tridiagonal matrix. So this system can be solved efficiently. Okay. But reason why that's not so great is if this is k by k, that means that the system that we're solving with each iteration is growing. And even though it can be solved efficiently, but still each iteration is incurring more expense than the last one. And we'd like to see if we can do better. Can we have an iteration where the amount of work done per iteration is about the same, which is actually what we had in steepest descent. And it turns out that is possible. We just have to dive deep under the hood and basically take its method apart and put it back together again in a different way. Now, one thing that can be done, and I won't get into the details here, but because TK is tridiagonal, and because the right-hand side is a multiple of E1, the first column of identity, it is possible to uses the fact that tk is tridiagonal to express yk in terms of yk minus 1 without too much work. And actually, that's something we'll take a look at a little later. So that's one way to make this method somewhat more efficient, but that's not the only thing wrong with Lanczos. Okay. Okay. All right. Because Lanczos is also, whoops, numerically unstable. Now, as I mentioned, the matrix QK has columns that are orthonormal, and that's and they're, but what I really mean is they're supposed to be, or theoretically, they're orthonormal. But everything is done with floating point arithmetic, which has some error in it. And what actually happens in practice is that we have what's called loss of orthogonality. Like you can check, like QK transpose QK is supposed to be identity. But if you were actually to implement Lanczos and try it out on some matrix A, you would find that QK transpose times QK is identity at first, but then it starts to deviate by a little bit, and then eventually deviate by a lot. Now, that is something that can be mitigated to an extent. You could use what's called Re-Orthogonalization to force the columns of QK to be orthogonal to one another. But that only goes so far. And plus, between the two of these things, we really want to see if we can do better. Can we have something that is stable and also less work to get each iteration? So we don't actually normally use Lanczos to solve AX equals B, because it is useful for other problems for which this method can be helpful, like finding largest and smallest eigenvalues, things like that. But for AX equals B, we actually modified Lanczos for a method that in exact arithmetic is mathematically equivalent, but in terms of efficiency and round-off error considerations, stability considerations, is much better. Because what we really want is this to behave like a typical non-stationary iterative method. We get each iterate directly from a previous one. Notice that does not happen here. xk comes from the initial guess, and then the combination of these columns. We'd like to say xk plus 1 is equal to xk plus some kind of update. And that's actually what we did have in steepest descent. We just don't have it here. All right. So how are we going to do that? It will not be easy. But basically, we're going to look at this system more closely. Now, what happens with this system from one iteration to the next? This is very helpful to understand what is going on and how we can improve it. Okay. So what I do is I'm going to write tk plus 1 in terms of tk. Now remember, tk is tridiagonal, and how do we get from tk to tk plus 1? We keep tk, and then we add a row and a column to it. And remember, it's tridiagonal, so we're going to have a new alpha here, because from the previous notes, tk had alpha 1, alpha 2 down a diagonal, and then betas down a super diagonal, and same betas down a subdiagonal. So it's just 3 entries going to add beta k in this spot, beta k in this spot, and then alpha k plus 1 on a diagonal. And then yk plus 1 is, we're going to break it down in a corresponding structure. So tk is k by k. So here we have a k vector here, and this is just a number. Now, I need to tilde here because I have no reason to believe that the first portion of yk plus 1 is equal to yk. In fact, it's not true. It's some other vector that I don't know about yet. So that's why I'm calling it yk tilde. Okay. All right. Now that I've broken down a system like this is a very helpful thing to do when you have an iteration going and you're solving systems of this kind of structure. What I do is I carry out matrix vector multiplication because here's my matrix, here's my solution, and then this is supposed to be equal to beta naught E1, which is the right-hand side for this system. So I do matrix vector multiplication, tk yk tilde plus beta k ek and then psi k plus 1, and that's what I have here. And this is equal to beta naught E1. Now, this E1 is the same as this one, except it has one element less. But I've already the same vector. It's a 1 in the first position, zeros everywhere else. Then I do the same thing with the bottom part. Beta k ek transpose yk tilde. And remember, that's a dot product, so that's a number. Plus alpha k plus 1, psi k plus 1. So everything here is a number. That's nice because I can solve this equation to get psi k plus 1. And then what I can do, and actually that's what I do right here. I solve for it right here. And then I can take this expression for psi k plus 1 and substitute it in here. And what that gives me is this system. So this system is a modification of this one. Notice it's tk tilde, yk tilde. Same right-hand side. And how do tk tilde and tk relate? Here's how. Because when I substitute this in here, then I have a yk tilde in both terms, and I can factor it out. And what's left is this matrix right here. So, so this system, what does this term mean? ek transpose is an outer product. Okay. ek transpose, being an outer product, is a matrix. Now, what is ek? Ek is a vector that is all zeros except for 1 in the last position. So let me write this down here. ek transpose, oops, that's lowercase k, matrix that is all 0 except for a 1 in the kk position. So the very last entry of a matrix, lower right-hand corner. So what does that mean? That means that these two matrices are equal except in that lower right corner, that kk entry, where this part, alpha k plus 1 inverse beta k squared, is being subtracted from that kk entry of tk. Now, when you're doing this, you take a matrix and you add an outer product to it, an outer product of vectors like this. That's called a rank 1 update. Very important term. It comes up in a lot of problems. And it's called a rank 1 update because this matrix, being an outer product of vectors, is rank 1. Rank 1 updates are very useful for describing very small modifications of matrices. Like if you're changing to just one entry, you can always describe that in terms of an outer product. Okay. Okay, I'll fill in a little more detail here for what I've been saying. that the vector ek is a vector that is 0, except the k or last component is 1. So emphasize it's a vector of length k. All right. Now, so how does this help us? Because all we're seeing here is that this first portion of yk plus 1, we now know what system it solves. So what can we do with that information? Okay. Well, nothing until we actually take advantage of a structure of tk and factor it. Because tk is symmetric positive definite and it's tridiagonal. So what does that mean? It has this factorization Ldlt. And I could use Cholesky, but Cholesky involves square roots, and I don't need that. So here we have an Ldlt factorization where L is unit lower triangular, D is diagonal. So this, and because it's tridiagonal, TK has lower and upper bandwidth equal to 1. So as you dealt with on homework 2, LK has a lower bandwidth of 1 also. So LK is just 1's down the diagonal, and then V's numbers here in a subdiagonal, everything else 0. And then DK has these diagonal entries here. And because it's symmetric positive definite, all of these are positive. Okay. And as I just mentioned, lower bandwidth 1. And that's going to be helpful to us too. Now, here's where things get more interesting. TK and TK tilde agree in all entries except for the KK entry here. So what that actually means is TK and TK tilde have almost the same factorization. The LK is exactly the same. Here we have DK tilde, only the kth diagonal entry is different. So this exact factorization applies to both TK and TK tilde, except for this entry right here is different in the two. And you can see that if you were to like multiply out LK, DK, LK tilde, you would find that everything you can make everything match up. It's just that you would only have to change this to get to affect the of the KK entry. Okay. Now, how we're going to exploit this so I'm going to define WK to be LK transpose YK, and then same definition of YK tilde, I'm going to call that WK hat. Now, my system I want to solve is TKYK as the left side, and this is the right side. So I replace TK with its Ldlt factorization, and then I have this right here. I've defined that to be WK, so I have that here. Then I do the exact same thing with TK tilde YK tilde, and that condenses to that. Now, notice in both cases, I have the same matrix to the left, LK. So now I'm going to take LK and move it to the other side. In other words, I'm multiplying both sides by LK inverse. Well, the right sides are equal. So these are equal. And they're both equal to beta naught LK inverse E1. But the other thing is DK and DK tilde are diagonal, and they're the same, except for the last diagonal entry. So what that means is WK and WK hat are exactly the same, except for the last entries. And if you were to write out the system of equations, keep in mind dk and dk tilde are diagonal, and they're set equal to the same right-hand side vector, how do we get wk or wk hat? All we do is we divide by the diagonal entries. That's why you can see that all of these entries of w hat are the same, except for the last ones. So, how am I going to make use of that? Here's how I get my iterates now with Lanczos. Xk is equal to the initial guess plus this. Now, here I'm doing a multiply divide trick, but with a matrix. So I have LK inverse transpose, LK transpose. So this is identity. But the reason I'm doing that is this part right here is WK. So I can write it that way. Okay. Now, what I'm going to do is, since WK is what I'm solving for, it solves this system. So now what I'm going to do is, I'm going to break down this system in the same way as I broke down this system, using the same block structure where I have the first k components and then the last component. Here I have a k by k block here, and then this is just a number. So same decomposition. What will that give me? Okay. Oh. Do I have this equation numbered? Oh, okay, this should be equation 1, so I'm just going to fill that number in there. Equation references don't work in this LaTeX editor, unfortunately. Okay. So what does that decomposition look like? Okay. Now, so what happens is, if I were to write out the entries of this matrix, I would see that the upper left k by k block is just this. And then the L's are unit lower triangular. The D's are diagonal. This whole matrix is lower triangular. So this part is 0, which was not what we had before. And then we have, okay. And then we have a last row of a matrix here. And then WK plus 1 breaks down as a WK tilde. And then this unknown entry here. Okay. Now, so what happens if I do the same thing as before? I multiply these out. I get LKDK WK tilde plus 0 times this. So I only have this on the left side. And that's equal to the right side that I had. And then I have this times WK tilde plus DK plus 1. WK plus 1 is the last element of a right-hand side, which is 0. Now, I don't really know what this vector is. I'm just saying this. I'm just referring to the first k components of WK plus 1. But what ends up happening is, if we look at how I define WK, solves this system here. LKDKWK is beta naught E1. Notice here, same system, same matrix, same right-hand side. Solution is unique. Therefore, WK tilde have to be equal. And what that tells us is the first elements of WK plus 1 are the elements of WK. Now, I need to state the most important point here. I want to emphasize it. because it really is the main idea that drives this whole algorithm development. Even though I still have a lot of other stuff to tell you, the essential idea has been laid out, but I need to point it out to you. The key difference is if we contrast this decomposition of a system of equations, like this system of equations, with this one, the key to the whole thing is this right here, this part of a matrix, which is non-zero in this case, but it's zero in the other case. Why? Because we worked with the Ldlt factorization of t, k, giving us in this system a lower triangular matrix that caused this to be zero. So what happened was, when we were dealing with the y's as to construct our solution, when we were representing our solution this way with yk, we could not say that the first portion of yk plus 1 was simply yk. It's some other vector yk tilde. Why? Because of this being non-zero. So that is what makes Lanczos less efficient. It cannot build on a previous iterate like we want to. So by working with this Ldlt factorization and just basically shuffling things around and working with wk instead of yk, causing a lower triangular system here, the first portion of wk plus 1 is wk. So that way, when we're trying to get this vector, an iteration k plus 1, we already have all of it except for the last element from our previous iteration. We did not have that before with Lanczos. So we just had to find the right way to organize the various factors in our system, group things together differently, and that gave us this change. So what can we do with that now? If I go back to how I get my iterates from Lanczos. So xk plus 1, this is how it's written before, except this is yk plus 1, and that comes from this definition right here. So I'm just filling it in down here, because really w I want to work with, not y. Next, what I do is I break wk plus 1 down into two pieces. The first piece is wk tilde, but that's equal to wk. So that's what I got from a previous iteration. And then here, this is the last element, the one that's newly computed during this iteration. I had to multiply by ek plus 1 because I need this to be a vector that is all zeros except for this in the last position. Now what I'll do is break up qk plus 1. Qk plus 1 has orthonormal columns. The first k of them come from qk, and then here's the one that's newly added on. Lk plus 1 can be broken down because it's a unit. This is a unit upper triangular matrix because of a transpose, and it breaks down this way where I have LK inverse transpose in the upper k by k portion. I have some vector here. I don't really care what it is. This is 0 because it's upper triangular. Also, it's unit upper triangular, so we know this is a 1. So then I'm basically taking this and distributing it through here, and then only for the first term, I break LK plus 1 inverse transpose down this way. Over here, I don't really need to do that. Okay. Now, what can I do with this? If I carry out the matrix multiplication, so actually, I think what I'd better do is actually fill that in as an intermediate step. Okay. Okay. So I have x naught plus. So first thing I'll do is, okay, I'll leave the q part alone for now. And then I want to carry out the matrix vector multiplication here. Okay, so I'll do that in a second. And then this last term, I'll just copy as is. Okay, so now I just need to fill in this part. So if I carry out the matrix vector multiplication, I get LK inverse transpose WK plus ZK times 0. Okay, so I have LK inverse transpose WK. And then in the lower portion, I have 0 times WK plus 1 times 0. So the last element is 0. So that's really convenient because now I carry out this multiplication. So notice it doesn't matter what ZK is. We literally do not need it at all. It can be whatever the heck it wants. And then, so we multiply this out and we'll get QK plus 1 will not be involved here either. So now we have this. And then we have this other term here. Now, here is another essential point. Notice how I have xk plus 1. X naught plus this term. Now compare this term to this one. Exactly the same, except the index is different in all three. In other words, that this part here, these two terms condense to xk. Everything I've done up to this point is with this goal in mind. This is the whole thing we were chasing. Xk plus 1 is now, new iterate is now equal to the previous iterate plus some update. Because that's how a non-stationary method ought to work. We go from one iterate to the next, and each iterate is just the latest one plus some kind of update. Now, with steepest descent, this is what we had, where we'd have some constant times a search direction. So we'd like to do the same thing here. We'd like to be able to think of this as finding some search direction and then multiplying it by an appropriate constant. So how can we extract that from this? So that takes me to the next part. But do you have any questions at this point? Or maybe you're like, huh? That's okay. It only gets worse. Okay. But we do have some essential ideas here, and that's even if you don't follow every detail, it's those main ideas that really drive algorithm development, because here they're applied to this kind of symmetric positive definite system, but they could also be applied in other similar situations. Okay. Okay, so now what I'm going to do is take a closer look at this matrix right here. So I'm going to make a definition. PK tilde is QK LK inverse transpose. It's exactly this matrix here, just a different index. And what does that give me? So if I multiply both sides on the right by LK transpose, then I would only have QK on the right side. Actually, I should fill that in here. Okay. And then on the left side, I'll have pk tilde lk transpose. So that's what I have here. Now I'm going to break pk tilde down into its columns, so little p1 tilde up to little pk tilde. And then here's lk transpose. We saw lk previously. It's just transpose now, so it's unit upper triangular. So now, suppose I carry out the matrix multiplication here. Well, what's going to happen is I'm going to go across these column vectors and then down one of these columns. Well, in each column, there's only two non-zero entries at most, a 1 and then one of these L's here. So if I carry this out, I get P1 tilde equals Q1. And then for all the other P tildes, I have QJ on the right side. And on the left side, this is what I get from multiplying these two. What this means is each one of these P tildes can be obtained by taking a corresponding Q and then subtracting off a multiple of a previous P tilde. So I have a simple recurrence relation from getting my P tildes from my Qs. So if I've already generated the Qs, then I can easily generate the P tildes with little work. I have to know what these constants are. So how are we going to use this? Okay. Now, one thing I want to point out, though, if I go back to my iterates now, what am I doing? I'm taking this matrix and I'm multiplying by ek plus 1. Well, that gives me the last column. So that tells me that I can write each iterate, whoops, as a previous iterate plus some vector pk that is a linear combination of one of these Qs and the previous search direction. Now, I want to emphasize, these P's are not exactly the same as the P tildes, but what I am saying is that they are parallel to them. So in other words, each pk is a multiple of a corresponding pk tilde. Now, the reason why I can say that is this turns out to be, okay, actually, I'll go ahead and write this in here so you can see this more clearly. Xk equals, okay, what's going on here? Oh, I see what happened. Okay. Sorry, I just darkened my screen by mistake here. Xk minus 1 plus, now what I have from before, I'll just fill this in, Wk pk tilde, okay, so it would be Wk, and then I have tilde pk, ek. So that is exactly what I had before. I've just shifted the indices throughout, and then this matrix product is a definition of pk tilde. Okay. Now, this is the same as x k minus 1 plus wk, and then I have lowercase pk tilde. That should be bold as a vector. All right, the last column of a matrix, capital pk tilde. So that's what I have. Each x is a previous x plus this scaled vector here. But what I'm going to do is I'm going to write it this way, because this exact vector, based on the definitions that are given here, is actually not going to be easy to get, because I don't actually want to compute the Ldlt factorization of tk, and I don't want to have to actually compute this matrix Lk and so forth. I don't want to have to actually compute Qk either. So I'm actually not going to try to get this vector. I'm going to try to get this vector that at least is a multiple of it. So these two terms will end up being the same. The products will be the same, but I'll have a different vector and a different scalar. That'll still get me to the same result. Why? Because I need a different way of getting this term than how this one was defined. Okay. So here's how I can do that. Well, first, the first search direction is just a multiple of Q1, because that's what I have here. P1 tilde is Q1. That is the initial residual. Now, the search directions, I'm going to scale these vectors anyway. So the vectors themselves, I can scale in any way that is convenient. And I'm going to take advantage of that liberty. So here's what I'll do. I'll just set P1, my first search direction, equal to the residual. Because I already know it's a multiple of it, I'll just set it to be equal to that. Then, subsequent search directions will be equal to the next residual plus some multiple of a previous search direction. Now, how do I know that I can do this? By comparing whoops, nope, that's not what I wanted to do. Okay. Okay. If I compare this equation to this one, well, remember, Rk is a multiple of Qk, so those are parallel. And the P's are also parallel to the P tildes. All the vectors in here, these two equations are parallel to each other. And so that's what tells me that I can set each search direction equal to a residual plus a multiple of a previous search direction. So all I need to know now is, how do I get this constant, mu k, that would play the role of this constant here? Because I don't actually want to compute this. I want to see if I can get this more efficiently. So really, that's the challenge now. I now have a way to get each iterate directly from a previous one, but I need to figure out what these constants are and these constants. Once I have those, I have my whole algorithm. Because I have a way to get my search directions give me my solutions. Okay, so here's what I'll do. If I take a look at this matrix here, pk tilde transpose a pk tilde, I can replace pk tilde with its definition, but then I use the property I seem to use every class. Transpose of a product is a product of a transposes in reverse order. So that gives me this. But qk transpose, that's tk. But tk has this Ldlt factorization, so I put that in there. And, ooh, like magic, these cancel. These cancel. All that's left is dk, which is a diagonal matrix. What does that tell us? Because this matrix is diagonal, If it weren't for the A here, I'd actually conclude that the columns of pk tilde were orthogonal. But we have this A in here, so I cannot say that. What I can say is they are orthogonal in a different sense. They are a-orthogonal, also known as a conjugate. Um, so, so what this means is, so another way of putting it, phrasing it, is this inner product, Pj transpose APK, is 0 when J is not equal to K. Now, if I didn't have A here, like if A was identity, that's ordinary orthogonality. But because the A is in here, it's A orthogonality. So what we found in steepest descent was that the search directions, each one was orthogonal to the previous one, but no orthogonality beyond that. And I remember saying at the beginning of Valancho's presentation, I wanted to have all search directions orthogonal, but that's not really practical. Here's what we have instead. All the residuals are orthogonal, because Lanchos gives us that. And the search directions, while not orthogonal, are at least a-orthogonal. At least that means they're linearly independent in a certain sense. Oh, wait a minute. Okay. They are linearly independent in the regular sense, but they're orthogonal in a different sense. So that's helpful. It means that, again, we're covering new ground each iteration. Now, because the search directions are a conjugate, and the search directions are obtained from residuals, which are gradients. Because remember, the residual is a gradient of a function we're trying to minimize at 5x that led to steepest descent. So here we have basically conjugate gradients. That's why this method I'm developing here is called the conjugate gradient method. But I still need a way to compute these constants. We need these constants mu k and nu k. Now, the way we can get them are from the orthogonality conditions we have. The search directions had to be a-orthogonal, and the residuals had to be orthogonal. Enforcing those properties will give us these constants. And I may not have time to show that in its entirety, but at least I've gotten to that main idea there, and I'll fit in as much as I can. Okay. Now, okay. I need to check my equation numbers here. Okay, 511, so equation 2. Okay. All right, so I need to fill in equation 2 here. Okay. Oops, I zoomed out too much. Okay. So what I'm going to do is I'm going to take this equation, multiply both sides by A, and then I subtract both sides from B. Then I can have B minus AXK. That's a residual. Here I have B minus AXK minus 1, also a residual. And I'll shift the indices also. So now I have each residual is a previous one minus this same unknown constant times APK. So now what I'll do is if I take the inner product of both sides of this equation with RK, remember residuals are orthogonal. The left side will be 0. So then I have the right side set equal to 0. I can rearrange it and solve for nu k. So now I have this formula. So that comes from requiring that the residuals are orthogonal. Okay. Another thing that I can do is I need to check my equation numbers again. 5, 12, so okay. All right, so equation 3. So what I'm going to, okay, I have yet another equation number. Okay, equation 4. Okay, let me zoom back in again. It keeps zooming out for some reason. Okay. Now, what I'm going to do to modify this formula is I can go back to this equation and rearrange it to isolate RK. So RK is PK minus this term. So if I fill that in down here, okay, so I'll write out what that is. Okay. All right, so RK is the same as PK. Whoops, not that RK. I want to leave that one alone. One down in the denominator. All right, so that's the same as PK minus mu K. Let me check my notation. Yeah. Mu K times PK minus 1. Okay. But the thing is, the search directions are A orthogonal. PK minus 1 transpose APK. This inner product is 0. So that's what allows me to simply change RK to PK, because they differ by a vector that is orthogonal to APK. Now I have this formula, and this is nice because we can see that this is guaranteed positive, because A is symmetric, positive, definite. Okay. Now, so we have a formula for one of our unknown constants, so we still need the other one. Okay. Again, gonna need an equation number, so that's equation 3. So if I take this equation, I need mu k now. So what I do is I multiply both sides of this equation by A. And then I take the inner product of both sides with PK minus 1. So, okay, so if I copy that, dang it. Okay, so I'm going to take the inner product of both sides of this. Well, first multiply both sides by A. All right, and then inner product of both sides with PK minus 1. Okay. Well, the thing is, again, search directions are A orthogonal. This is 0. So now I have this whole thing equal to 0, and I can rearrange this and solve for mu k. Remember, these are all inner products. They're numbers, so we can certainly divide by them. So now I have a formula for mu k. Now, that's something, but I want to try to simplify that if I can. Okay. We're just about done, I swear to God. Okay. So, okay. which is equation 5. Okay. All right, so if I use equation 5, because if we look at the formulas we have now for mu k and vk, I need ARK, I need APK, and APK minus 1. So I need to multiply A by the residuals and the search directions. That means I need 2 matrix vector multiplications per iteration. I want to see if I can get away with just 1 matrix vector multiplication, because that's going to be the most expensive operation that we need. So here's what I do. If I go back to this equation right here, I can solve this for APK. It's RK plus 1 minus RK divided by this negative constant here, negated constant here. So then what that lets me do is fill this in here. So this comes about from solving this equation, index shifted. So in other words, I subtract 1 from all the indices. So I have APK minus 1. So I use this equation to eliminate APK minus 1, this one, from here. So now I have as a difference of residuals. But remember, all the residuals are orthogonal. So RK minus 1 transpose RK is 0. So now I have just this in the numerator. Similarly, I take this search direction and use a formula for it. And here I have, again, A orthogonality. PK minus 2 transpose APK minus 1 is 0. So this term goes away. And now I only have this term. Here I have APK minus 1 again. So I use the same substitution that I used up here. Residuals are orthogonal. RK minus 1 transpose RK is 0. So this term goes away. Now I have these two constants, nu k minus 1 inverse, above and below. They cancel. This is all that's left. So now this formula from UK, far better than this one because it requires no matrix vector multiplication at all. I still have one for nu k. Can't do anything about that. But at least I made so. Even though you have something here that can work, it's worth using whatever facts you have, like your orthogonality of certain vectors and so forth, to see if you can eliminate matrix vector multiplications, thus getting a more efficient algorithm. And now I finally can show you the actual algorithm. Never thought I'd make it. Okay. So this is a conjugate gradient method. So after all I showed you, it seems like this is not very much, which is what's so nice about it. It's the end result. There's a lot. It's pretty painful to get here, but the end result is fairly simple. So you get your first residual before you start, and then during your first iteration, your first search direction is your first residual. Then you just need to compute the coefficient nu k and now you have your first iterate. It comes from your initial guess, which could always be 0. The same constant nu k that you use to compute x also gives you a residual. Then you keep going, and for subsequent iterations, you get each new search direction is your residual plus this constant times the previous search direction. So you keep updating your search directions, and then you keep updating your iterates accordingly. Notice this is the only matrix vector multiplication that's needed in each iteration. So the algorithm is quite efficient in that respect. And generally, this kind of method is used for sparse matrices. So matrix vector multiplication might only take like order n operations. Okay. Whoops. We need to have a stopping criterion. Like for instance, if a residual is particularly small, that would be one example of a stopping criterion. It's a good idea to have a maximum number of iterations. But what's interesting is if A is n by n, theoretically convergence should always occur within n iterations. Because all residuals are orthogonal. Once you have n residuals, you've taken up the whole space. The next residual would have to be 0. But this is generally used for large system equations, very large value of n. So you'd want to have convergence in far less than n iterations anyway. Okay. Okay, and actually that leads to me next properties. Oh, it's okay. Yeah, so convergence in most n iterations, at least in exact arithmetic. So in fact, when Hessides and Stiefel invented conjugate gradient, they didn't think of it as an iterative method. They thought of it as a direct method because it would produce the solution of x equals b if you ran it all the way to completion, to n iterations. But it turned out to be numerically unstable, just like Lanczos was. So back then, when it was invented, it wasn't actually used. It was so people, because it wasn't really as effective as Gaussian elimination, but in the 70s, it found new life, and as an iterative method. So the idea is you don't let it run all the way to iterations, and therefore avoid that stability. Okay. Oh, okay. I should mention that when A is ill-conditioned, conjugate gradient can still converge very slowly, may not be very effective. So what you do is what's called preconditioning. And I won't really get into that. That's actually the next subsection. And you end up modifying this algorithm where you end up solving a system involving a sparse matrix. That's called a preconditioner. And preconditioning is actually a very active area of research in numerical linear algebra, like trying to find effective preconditioners. And you basically want to transform the AX equals B into a new problem where the matrix A is closer to identity and therefore better conditioned. And there are many different approaches to doing it depending on the problem, but it's generally not easy to do. But for it may be something that's very problem dependent. And actually, well, I know that I have one of you working on preconditioning now for a particular problem. So they know what a pain it is. Okay. So there's a MATLAB function. There is no MATLAB function that's just CG. It's actually PCG, precondition conjugate gradient, where you supply an optional preconditioner. Okay, so that ends conjugate gradient. On Monday, I'll be spending one more day on iterative methods, showing some other iterative methods for problems that aren't necessarily symmetric positive definite. So certain variations on conjugate gradient that still use this idea of Krylov subspace methods that was used to derive the Landshell's algorithm. Okay, so my apologies to those whose brains are completely fried and now have to sit through PDE. That should be a whole lot tamer than this. We still have a few minutes for any questions that anyone has. Thank you, Walker. For I think trying to understand conjugate gradient can lead one to pull one's hair out, so that's one way to solve a problem. Oh, yeah. Okay. Well, I think we're on hair now, so it's probably a good idea to end. So, um, okay. So I'll stop recording at this point, and we'll see some of you in PDE, and hopefully you have some brain cells left.